Yeah. Okay. Thank you so much. Hello. Welcome to the NYU Tandon School of Engineering and the latest presentation in our seminar series in modern artificial intelligence. The series aims at unifying scientific communities around the influential research ideas of today that we predict will have a major impact tomorrow. AI is already recognized as an important topic of research with applications in medicine, biology, neuroscience, and other vital fields. And we hope that the scientific discussions that result here will contribute to building a better world and promote groundbreaking discoveries. I'd like to thank Dean Jelena Kovacevic for her strong support, as well as my own Department of Electrical and Computer Engineering for hosting this series, which has evolved since its launch into a respected and significant event in the AI world. When I first conceived of the series, I hoped that I would be able to attract highly esteemed speakers doing revolutionary work in their respective fields. I will say, with some humility, that I have succeeded beyond my wildest dreams. Our guest today is a perfect example. Alex Smola studied physics at Munich University of Technology and computer science at the University of Technology in Berlin. He received a PhD in 1998. He subsequently joined the Australian National University and National ICT Australia, now part of Data 61 at the Commonwealth Scientific and Industrial Research Organization. He served as full professor and group leader there until 2008, when he joined the staff of Yahoo Research. His CV includes other iconic names as well. In 2012, he made the move to Google, and from 2013 to 2017, he was a full professor in Carnegie Mellon's machine learning department. In 2015, he founded his own company, Mariana's Labs. Since 2016, he has been a VP and distinguished scientist at Amazon Web Services, where he builds AI and machine learning tools for everyone. In addition to well over 500 journal papers, he has co-authored several books, including most recently the 2022 volume, Dive into Deep Learning. In the realm of AI, he's an absolute superstar, and we are very lucky to have him today. His presentation is compellingly titled, Empowering Multimodal Auto Machine Learning for the Next 10 Million Users, which will delve into the tantalizing promise automated machine learning offers for translating raw data into accurate predictions without the need for significant human effort, expertise, and manual experimentation. I know none of us can wait to hear it, so without further ado, I give you Alex Smola.
Thanks, Anna, for the kind words. Before we proceed, I guess I need to first click away this acknowledgement that the talk is being recorded. Yeah. Okay. Okay, I guess we knew that. And yeah, so this is a bit of a summary of what one of my teams at AWS has been up to over the past 2-3 years. And well, I know those slides have aged about as well as fine milk, given that at the moment Silicon Valley has decided that they've overhired. But nonetheless, so in 2022, Amazon hired over 55,000 new tech hires. So by the way, so put that into context with the number of people that unfortunately were let go, it's still a net plus of over 35,000 people, right? So the demand for people who can do, amongst other things, machine learning, and I would say by now any new hire should be capable of doing that, is actually quite significant, right? And the problem is that the supply of people who actually are trained in machine learning is not catching up with this. If you look at, for instance, North America, then the order of 400 AI PhDs per year in North America, right? This is one fine example of a school that produces great PhD students and great master's students and undergrads. And so if you look at the undergrads, you have about 30,000 CS undergrads in North America per year. So what that really means is that there's a lot more demand and need for people who are machine learning competent than there are people out there who are. And one way to fix it, and this is, for instance, what we've tried to do with Dive into Deep Learning, is to make it easier to learn things. But learning requires effort on behalf of the audience. And so the question is, can we also do it by just making things easier? And I would argue that we've gotten really far. And yeah, maybe I should be adding another line into this, including ChatGPT, as in, here's some text and zero-shot learning. But basically in 2012, and this was PhD level homework, this was the most difficult homework that I taught in an advanced machine learning class in Berkeley at the time, just implementing a large linear model. And with large linear model, I meant like 1 million parameters, right? This was really, really hard. And these were very, very bright students, some of which have gone on to become faculty and all of that, right? In 2017, so 5 years later, maybe even 2015, 16, implementing a computer vision model as part of PhD level homework, yeah, that's fine, right? I mean, this is the time when, GoogleNet and ResNet and so on started getting popular. You could, go and download code online. You can implement LeNet itself in maybe about 12 lines of PyTorch or Keras or MXNet or TensorFlow, or even, well, Caffe takes a bit longer, but basically you can do that fairly concisely. And so you can, hand that out as homework. And we did this at CMU and the students did fine. They didn't complain as much as the Berkeley students. Maybe CMU students are tougher, but I would argue it was easier. And then in 2021, well, we basically told undergrads in Stanford to, solve some NLP task as part of the homework. And they did quite well. And they didn't complain much either, probably less than the CMU students. Again, you could argue maybe Stanford students are smarter, but I would argue it was just easier, right? And these are undergrads. Well, why do I say that? Well, if you look at those 3 lines of code below, this will give you a high performance tabular estimator, so basically on tabular data. And I'm happy to challenge you that it will take you more than a day to beat this if you have to build it from scratch. Okay. Now, I'm not just claiming that. I did some human experiments on my own. I have, now 17-year-old, but at the time he was 16 years old. And for some project that he was doing, he needed some time series model. I mean, he screwed up the time series part, but that's besides the point. But basically, I told him, okay, here's some documentation. The only help that I gave him was how to set up Jupyter with remote in the cloud. That was the harder part. And I told him, okay, go forth and do this stuff. And he actually got it running. And apparently, the people who looked at it liked it. So this is basically now a teenager can build a pretty competent tabular predictor because they don't need to understand anymore really what goes on behind the scenes. So this is good, right? So the question is, are we there yet? So let's look at where we currently are. And those numbers are already, again, a little bit dated because they're already half a year old and stuff moves. But the important thing is we didn't do this benchmark, but Peter Geisbers did that as part of his PhD thesis. So Peter Geisbers, this guy, decided to actually build an AutoML system called Gamma. And I must say huge props to him to evaluating it against everything else. And the fact that you haven't heard of Gamma probably is clear from this plot. So this is essentially looking at 104 data sets, 10-fold for our training limit, and looking at the relative ranks of those 10 different alternatives, right? And the average rank for AutoGluon is pretty decent. It's like around 2.8, and it's way better than others. Those solid bars are error bars, and for where you can statistically distinguish them, you could probably tighten up those bars further. So maybe those rings will get narrower, but by and large, it's clear that AutoGluon is doing something fairly well. Let's dive into it in a bit more detail. So this is for binary, multi-class, and regression, and also for 1 and 4 hours limits. And the question that you might ask, what are those time limits? Well, those time limits are there because you need to actually solve a problem within a given amount of time. And very rarely would you be given arbitrary amounts of time to solve a problem, right? And there are other studies for, if you spend even more time, what you can do with accuracy and so on, and the picture would look pretty much the same. But what you want to see is essentially how well the system does relative to, the best performance. And the important part here is two things. First of all, actually AutoGluon does fairly well compared to all the other things, but also the error bars are fairly small. In other words, the chances that occasionally you might get really badly disappointed are very slim. And that, I would argue, is just as important as the good performance. Namely, you want to make sure that you don't get occasionally a really bad surprise. And last but not least, it's also very fault tolerant. So in 2080 different data sets, so it's actually really those 104 data sets, and then looking at, in this case, 20 different configurations. So basically different splits. AutoGluon fails in only 3 out of those cases. And these are out of memory cases where we just, use more memory than what that test instance that Peter Geisler set up allowed for. So that's quite useful. It's useful because, again, if you want to deploy this, the last thing you want is that you deploy it and you find out that it crashes. Okay. So to give you a bit more of an idea of, how this looks like, in terms of, the bigger picture. So the x-axis is log of prediction speed, because you don't only want to have high accuracy, but you also want to have it run fairly fast at deployment. And again, results courtesy of Peter Geisler's thesis. So he did us a solid for really advertising. And what you can see is that over time, so from version 0.1 to 0.3 to 0.5, AutoGluon has gotten more accurate, but it's also gotten slightly faster. Furthermore, we started adding high speed settings where, so this is the arrow on the very left, where if you are willing to trade a little bit of accuracy, so basically it's the same accuracy as what we had about a year and a half ago, we're now 80 times faster. So this is useful simply if you need to solve problems quite efficiently. And by the way, there's a couple of people who like to brag about all you need is XGBoost. Well, XGBoost isn't even on this plot, right? The accuracy of XGBoost is much worse. Sorry, it doesn't. Yeah. So this is a slightly bigger picture, and this is now including, more up-to-date versions, so version 0.6. So basically the picture on the lower left, so the red circle on the lower left, that is the very best XGBoost version. I mean, yes, it has higher throughput, but it has much worse accuracy. So now you want that normalized score. Well, the issue is basically if you have a whole bunch of classification and regression data sets, you need to somehow, compare all of those, because for regression, right? I mean, you, for instance, want to scale it to, have some well-defined loss. So for instance, what you could do is you could just make it so that the overall variance would be, a score of 1, and then you look at, loss relative to the worst possible thing you could do. Now, here's a little bit of a heads up of what's coming. We decided to push a little bit further in terms of higher accuracy. And so basically, if you go and add transformers also make AutoGluon better. And so that's coming, well, it's in pre-release, but it's going to be probably in the next 1 or 2 months that it comes out. And this gives you a little bit of an idea of where the Pareto frontier is. Let me actually show it to you on the picture here. So this is where AutoGluon is right now. This is the preview out in probably about a month or 2. This needs GPUs. Unfortunately, everything else here was CPU bound. And here you can trade off speed versus accuracy. This is H2O, and yeah, that's H2. To give you a bit of a lay of the land, we're not quite as fast as PX2 but that's what you get. Now you might ask the question, well, isn't there something like, for instance, Frankfurter's tabPFN? Yes, absolutely. And tabPFN, for instance, are one of the components that go in. That's one of the reasons why we get the lift from here to there. It gets slower and more accurate, but it's also more accurate than tabPFN on its own, because it's using assembling and bagging and so on as an overall wrapper around it. Okay. So this is, by the way, the secret why we managed to get good accuracy, because it's not a monolithic system that just uses, a single algorithm and tries to tune that as well as possible. But we combine pretty much anything that works. And if somebody else comes up with a good idea, thank you very much. We'll happily integrate that. And so, we make progress. So I hope that somebody here will come up with an idea of how to beat us, because we'll happily integrate it. Okay. Now, with that said, the question, of course, is, does it work better than humans? And here's an experiment that we ran. I mean, we didn't really run the experiment, but Kaggle ran it, right? So you can reasonably well assume that if you're participating in a Kaggle competition, you're trying to do it to win. Well, maybe not everybody, but what we did is we looked at the 10 best teams in the Kaggle Auto competition, right? As in the 10 best teams at the very end, and you can assume that they probably were semi-serious in participating in that competition, right? And you can also see that by, so this diagram on the left is time versus accuracy. You want to be as low as possible, right? That's high accuracy. And this is, each of those lines. And so you can see how, as people improve the algorithms, they keep on getting better. And, they have fantastic names like team names like I don't know, or team, or optimistically convergent, but whatever. Team I don't know apparently won in the end. Okay, fine, doesn't matter. It took them about maybe, the competition ran, I think, 2 months or so. Now, here's what you get with AutoGluon. This is version 0.4. By now, it will be slightly better still, but you get an accuracy of 0.399. Okay. You get that after 4 hours, and it takes the best human team about 6 weeks to get to the same level of accuracy. So I'm not And in the end, I mean, we score at the rank number 14, and probably by now with version 0.6.1, we would be slightly better still, and with Part 7, we will be better still. And yeah, I mean, if somebody wants to run the experiments, by all means do so. But the key point here is that within a matter of hours, you get to a point where a competent team, and you would argue that, you know, if they won a Kaggle competition, they're probably somewhat competent in machine learning, got to within about 6 to 8 weeks. Now, in practice, this is super useful because in practice, you're being hired to solve a lot of problems, at least in a company, right? And you can spend 6 to 8 weeks on solving a problem, or you can spend 6 to 8 weeks on solving maybe 10 problems. And at that point, it's not just accuracy that matters, but also speed. And mind you, you can take the results that you get from AutoGluon at this point and then optimize further, optimize for the variables, optimize for dependencies, data sets, and so on. So it's not that, you know, you go and spend the remaining, you know, 5 weeks and 4 days in a coffee shop, you know, just having fun. I mean, you're actually going to do other things then to improve things. So it just means you can either get further on the accuracy scale, or you can just solve a lot more problems. Now, it gets you the same thing on a whole bunch of other competitions. So I'm not going to go into a lot of details there because, well, they're all kind of the same flavor. But the key point is really, with those 3 lines, you're pretty much done for tabular data. There's a tiny little, there's a tiny little caveat, and the tiny little caveat is that if you have billions of observations, then probably you still have to do a little bit of extra work, and that has a lot to do with the fact that we use bagging and other things. If you have such a large data set, please let us know, and we'll happily work with you. We just didn't get a lot of those cases where people actually complained about scaling limits on tabular data. For text and images, it's a different story, and we'll get to that in a moment. Because after all, this is about, you know, also text and images. Anyway, so here's a little bit progress over time, and that also gives you an idea of, you know, how those projects evolve. So in March 21, so 2 years ago, and this was, you know, we got like 70% win rate over previous releases. We added multimodal tabular and text support. We added past AI and XGBoost. And yeah, those things all worked. Point 2, basically people complained that we used way too much storage and inference ran too slow because basically people inside Amazon started using it and they said it's too slow. And yeah, we started talking to NVIDIA, and thanks to NVIDIA for Rapids, and that helped a lot. Point 3, again, much faster online inference. For images, I mean, adding TIM. So this is getting towards, you know, what you would do with foundation models and pre-trained models. You will get much better, you know, performance again. And what was also really important was custom model support. And custom model support was important for 2 reasons. First of all, it's the if you can't beat them, join them strategy where, you know, sometimes we would go to a team and they're like, yeah, okay, we tried AutoGluon and it works about the same as what we're currently doing, so we're not going to change things, right? And there's always a really strong incentive for whatever incumbent team not to do anything because that's the easiest thing and it's job security, right? So if you have a team of 3 to 4 people and they've been hacking at a problem for years, then, you know, they may have a really convenient job and like things the way they are. So if you say, well, I'm going to replace you with a little script, they will feel apprehensive. But if you tell them, okay, well, look, all the great work that you've done so far can be now part of this larger AutoGluon system. And by the way, it's now one of the models in the custom models. You're no longer their enemy. They will actually happily, you know, adopt it. it may very well turn out within a few months that the custom model gets 0 weight, but that's no longer our problem then. That's their manager's problem. And yeah, I know it's silly, but sometimes psychology matters. So then point 4, again, a lot faster inference. Then, we started actually using multiple machines. So mind you, up to that point, a single machine was more than good enough. Hugging Face helps a lot for text in this case. That was basically a year ago. Time series, that was the big change in point 5, and much better multimodal, and I'll get to that. And then point 6, a lot more objective functions, named entity, there'll be ranking in it soon, model compilation. So basically turning this into a much more rounded deployment toolkit. The reason I'm showing this is because it also shows that there's still a lot that needs to be done. And to some extent, me being here is also an invitation for you if you want to contribute. Since it's open source, well, join us. And things have been getting more lively. So this is GitHub commits, and yeah, there's something happening every day. So we try to have about 4 releases every year, so approximately every 3 months. So rather than waiting for the very best release, we just try to make sure we keep it moving. And if a feature doesn't make it for something, it'll just make it to the next release. Okay. So far, this is tabular data, and I think by now tabular data is under pretty good control. There is still scalability issues if you have, many billions of observations. If you have such a data set, talk to us. There's probably still a fun paper to be written. Now let's look at real data. So I don't know whether you're in the market for buying Amazon sofas, but that's what this thing looks like. Yeah, there's some title text, and because it would, and a color, and it costs some money. That changes probably over time. There's actually more than one image. There may be dozens of images. And then there are lots of features like how heavy it is, how big it is, and all of that. And so the question is basically, how do you deal with this data? Because this isn't just, your standard tabular data where you have a bunch of numbers, but it's, a variety of stuff. And for a lot of this variety, well, we have prior knowledge. So we've seen pictures of sofas before, and we've read text before. And then you get an image like this. And so the question is, for instance, that you might want to answer, is this the same sofa? So why would you care about whether that's the same sofa? Well, for many products, you may actually have multiple sellers selling the same item, and you want to group them together. And you want to find out whether it actually is the same item. At the same time, you also want to make sure that people don't start selling bicycles on a listing that was previously listed as sofas, right? And sometimes that still happens, but yeah. So here's an example of, well, something that's not quite the same sofa. It looks very similar, but it's not. So, these aren't entirely trivial problems. But the point is basically real data is really messy. So you have tabular stuff, you have like page views, item price, weight ratings. You have a lot of different pieces of text. And yes, okay, you could just say, throw it all into a transformer and the great transformer will solve it. Yeah, been there, done that. You can do better, and I'll get to that. You have multiple images, and then you have a lot of domain-specific things. And so the point is basically, can we combine all this data into a good model and use the prior knowledge about the specific domains to do a good job, right? So here's what a multimodal data frame might look like. You might have a label. You have a whole bunch of tabular stuff, and then, for instance, you have pointers to images, and you have some text. And so, well, how do you actually deal with that in practice? Let me first show you the API, and I think this is important because we are targeting an audience that isn't necessarily very machine learning savvy, right? We're targeting an audience of, undergrads. I mean, basically, my now 17-year-old son is, a not unreasonable target audience. He's an okay programmer, and his machine learning skills aren't so great either. Okay, maybe I need to do something about that at some point. But basically, yeah, it should work for him and maybe smart undergrads. So all you do is you just import the multimodal predictor. We go and pull pre-trained models from wherever we can get them. Hugging Face has done a great job at making that easy. Tim, by now, I mean, they basically hired Ross Reitman, so Tim is getting integrated in Hugging Face too. It was a smart hire of Tim. And then all you do is you just invoke a predictor. And in this case, for instance, here we want to find out, what the final status of, whatever product was. So we pick that column name. So, and then you run a fit function. So that trains things, and then you predict. Now, if you want to do a little bit more by also using assembling and so on, so this is basically not just using your deep network, but for instance, for all the tabular part, how do you actually combine the models? And I'll get to that in a little bit more detail as we go along. Then you just invoke the tabular predictor. Otherwise, the call signature is pretty much the same. It will do some parameter tuning, but again, the API is very simple. Now you might think, well, this is really, very convenient but monolithic. The good news is you can unpack all of that. So this is just, I'm showing you the batteries included version, but it's batteries included but removable. So you can go into as much detail and custom configuration as you want. Now, obviously, no machine learning talk is complete without these guys, right? Foundation models. Yeah, okay, I should have rerun this through maybe Stable Diffusion, but whatever. Yeah, so, there's a lot of models out there. And this list keeps on growing. I think by now there's a tracker just on large foundation models for text of which ones are currently available, and it's a new one every few days. So the point is, you want to have this reasonably modular, such that if a new foundation model for text comes along, well, we can just go and happily grab it and add it to whatever we are doing and get high accuracy. Right? So this is from end of last year. So Hugging Face at that time had around 77,000. I think by now they've crossed the 100,000 models mark, and Tim has probably 650 to 700 models too. So usually AutoML doesn't use model zoos, except that well, we do. And again, this is the point. The point is, if you have a reasonably novice user, they don't necessarily know which of the models you should be picking, right? So, if this is this famous picture of, various models, and I think the graph is from 2019 or so, which one do you pick? Well, the first thing we have to do in order to evaluate this is to actually make ourselves some benchmarks. And if you have nice benchmark data sets for tabular plus AutoML plus multimodal data, please send it to us and we'll happily add it to it. So reach out to Shingen or via email. So if they have additional data sets. So they're not as common as one would think. They're very common in practical settings if you work in a company. But the problem is most companies don't want to release that data to the public because it's, commercially relevant. And a lot of the data that you're seeing in academic competitions, it's only text or it's only images, or if it's text and images, it's in some very stylized manner. So for instance, if you look at Lion 5B, I mean, it's a fantastic data set, 5 billion images with captions. I mean, years ago, you would have dreamt of this as, this is crazy. I mean, who could pull this off? But in reality, what you actually have is you don't just have images and captions, you have the URL where they came from. You may have EXIF data in the images. So if you know that the photo was taken with an iPhone versus, a Sony A7R Mark V, so in other words, like a $4,000 or $5,000 camera, you can already infer from the fact that this was taken with a $5,000 camera that the person using it probably knew what they were doing. Okay, exceptions exist. I have a fancy camera and I'm probably not a very good photographer, but in general, if the camera is expensive, you know that the person probably spent some effort taking photos. Whereas if it's, $100 throwaway phone, you don't know what's going to happen, right? So, or if you have the GPS location because it's taken with a mobile phone and you're trying to do object recognition and you can see that it was taken near the Eiffel Tower. Well, what are the chances that it's off the Eiffel Tower, right? So those things are all additional pieces of side information that quite often people disregard, but it can give you a significant boost in accuracy. Anyway, so let's look a little bit at, what you could do. And the first answer would be, yes, transformers are the answer to everything, right? And being there, try that. And it works okay, but it's not as great. And sometimes you get papers which are of the form of a strong baseline for X. And the a strong baseline for X by now usually turns out to be a transformer model, right? So in other words, you take text, you throw it into a transformer. If you have anything but text, you turn it into text and you throw it in. Okay. And it works all right. If you have multiple segments of text, throwing that all into a transformer with maybe appropriate headers and separators, that's actually quite effective, right? So, because, well, humans are good at that and transformers are for language are trained on a lot of the same kind of data that humans are good at. So you can assume that they learn reasonable representations. But then once you have, other data types, so for instance, you have images and maybe you have some tabular data and so on, what you can do is you can basically perform early fusion, where you just map everything into some representations and then you run another transformer without the tokenizer, or you basically go and do essentially multiple tower models, and where you have a lot of processing and only in the end you aggregate. And so at the end, well, you've got to try out what works. It turns out that late fusion actually works quite well, and that's good news because it makes it a lot more modular and componentized to test things out. Now the point is, I'm not just saying that because I believe that one is the case or the other, but we just ran experiments and we picked the better solution, right? Now, if you then want to use XGBoost and other things in combination with that, you basically take the outputs of your first layer of your model, and then you perform the appropriate stacking with XGBoost and other tabular tools on top of these outputs. And this way, you get all the nice non-parametric strength of a tab PFN or an XGBoost or a combination thereof, in addition to all the power that your foundation models bring you. I know this looks like Frankenstein, and it's basically training a mix of maybe nearest neighbors, decision trees, neural networks, kernel methods, and 5 other things in some abominable stage-wise procedure. But if you're reasonably careful, you can, despite stacking, actually avoid the overfitting. So stacking just means you take the output of your predictor and you now use that to train another predictor. And you could easily see how that could overfit because you're now training on the labels, right? But what you're doing is, since you're doing k-fold k-fold prediction, right? You basically use the predictions on the fold that you left out as the features for the next prediction stage. And this way you ensure conditional independence. Sorry, this is going a little bit fast, but it's just because entire talk on its own. And by setting this up, you can make sure you don't overfit at least for 2 levels of this architecture. And so you get a little bit of extra accuracy at the expense of not that much extra cost because you paid the huge cost of running your transformers once. So you're basically executing, all your foundation models only once because that's very expensive. But then anything that's cheap, like, that you can easily bag and boost, well, you can run multiple times on top of that. Okay. So now the next thing that you may need to worry is parameter efficient fine tuning, because in some cases, well, you do have just a large model. And why did we get into this? Well, it's because, well, sometimes you do have just a large NLP task or a large vision task. And so I'm oversimplifying here what a transformer looks like. And this is really from the He et al. Paper. It's basically a giant matrix multiply. And so what you can do is you can essentially, fine tune the bias terms. You can, or you can, just mess with the output. That's called an adapter. So basically you add a low rank plus nonlinearity version to the output. You can do that from the input. It's called prefix tuning because, well, you got to give it a different name so you get a separate set of citations. Or you can, drop the nonlinearity and you rescale this. So basically just low rank, again, separate name. And then you can call it a parallel adapter because, yeah, okay. Again, you need to have a new name or scale parallel adapter. But basically, these are all minor variants on the theme. The point is, you can try them all out. And we actually have a paper that's coming out at ICML about how to do some reasonable model exploration in terms of basically which of the optimizations you should do. TLDR, you should use all of them. You should spread your capacity fairly evenly. And that's a pretty good idea. But the specific optimizations may very well differ depending on the first few, the middle, and the later layer of your transformer architecture. But in any case, so you can do all of this, and then you get a pretty good fine-tuning system. So more to the point, you can get essentially as good accuracy as full fine-tuning if you were to optimize overall parameters using only 0.5% of, all the parameters in the system. And just as importantly, what this means is you can do that on a consumer grade NVIDIA GPU. So you can get 11 billion parameters happily fine-tuned on a 24 gigabyte GPU. So your RTX 3090 or 4090 will do just fine. And you don't even need to run anything on an expensive A100 or H100 server. Okay. Now, here's just putting it all together. So this is one of those data sets. Apparently, estimating how long it takes to get cats adopted or animals in general is a thing. So I guess this is a cat that only its adopter could love. Anyway, so he's apparently a cat that needs to find a home. So you run the text through some of the Hugging Face foundation models. You take text and images, run them through CLIP or anything similar. Images themselves, just a pre-trained model with Tim, and then you use a tabular transformer for the tabular data, and you fuse it all together, and you're done. So how well does this work? This is the Hugging Face graph leaderboard, and this GPT-3, probably version 1. I don't know where we are, but this is where we were in September. Then we use better backbone and better fine tuning. This is automatically solved on the RAM leaderboard. At least late last year, we were the #1 spot there. Probably by now somebody's got the speed, but what this really shows you, I hope, is that you can get by now fairly far using AutoML and using a lot of those tuning methods. The reason being simply because most humans don't have the patience of trying out 20 or 30 things. Whereas in an AutoML system, you code up an idea once, and then you just apply it every time. And this is also why I would very much like to invite you to join this effort, at least, with your latest work. If you have something good that beats the accuracy, add it to the set of components, and then it gets deployed everywhere. Okay. So what do we need to do to make AutoGluon even better in the future? Well, it's really more of everything. So we need to get better data ingest. We need to have better GUI modeling, better visualization of the results, automatic problem detection. So right now we do, I think, a decent job between regression, classification, or multi-class, but there are a lot more problem types that would be nice if the user didn't even have to specify what exactly they wanted to do. There's a lot more that can be done on the labeling side, so active learning and so on. Fairness, there's pieces coming there. We always want to make things faster, more device support. And then what would be really nice is also have like an online prediction endpoint. So where just you say, well, I stand up an instance, I keep on feeding it data, and it just keeps on coming back with better predictions. Just on the parameter limit, I guess everybody's seen that picture, and it's basically, this exponential increase in the number of parameters over time, right? And I just drew for reference the lines of, how much memory you need in order to run those models. And you can clearly see that, things are getting a little bit tight. But it also tells you that, 10-ish parameters is about the limit of what a consumer card can currently handle. So that's why we picked that. And by now you can tune up to an 11 billion parameter model on a single GPU. Part of the reason why this works is great in checkpointing, pushing things back into memory. It's not the fastest thing, but then if that's the only thing you have in your office as a PhD student, right? Because that's probably where the sweet spot in terms of price and noise and heat generation is, right? Then at least, you can be productive. There are other pieces in there, what we do just to make sure that, stuff runs fast. There's distillation in there. There's a lot of tricks on, how you construct appropriate data to distill on. I mean, distillation is a fancy word for function approximation. But of course, if you call it distillation, it feels like a new paradigm. But all you're doing is really, well, I have a function. It does a good job. I have a domain on which it needs to do a good job. So now let me estimate another function that is as close to the original function as possible on that very domain. And so you need to have a good way of, sampling from your domain, and then you need to optimize. And okay, that's basic distillation. I know Geoff Hinton will kill me for that statement, but it's just function approximation. there are other details in there where you can use it to essentially hide DC programming in, self-distillation or teacher student and momentum, but that would be a separate talk. Anyway, I'm going to skip the time series because I think I have 2 minutes left. But basically time series by now is there. Just one more quick thing. Well, what if you didn't need to actually install AutoGluon? What if you could actually run it in your browser? And so basically, if you didn't have to do pip install and all the stuff and set up Python, and maybe on Windows it's a pain. So very soon you'll be able to just run AutoGluon directly in your browser with about a 3x speed penalty. The reason why this works is basically Pyodide and PyScript. So by now people have figured out, thanks to the Pyodide team and also the Anaconda team, how to abuse the JavaScript engine of your browser to run Python. And we happily took advantage of that. And so by now a subset of the models can easily run there. And what that just means is that at this point, you can then at least do very quick tabular models there. I mean, don't go hoping for transformers, because running transformers in your browser, okay, we'll have to wait for better support from the likes of Google and Apple, or maybe Microsoft. But of course, all of this is courtesy of the team here. I mean, they did the actual work. I'm just the guy who's here and talking about it. So Nick, Xingjian, and Alex, they did the hard work, but there's also Mu, Ryan Tipshirani. So Ryan helped with model calibration when Ming is the PM. Yep, it's a lot of people who put a lot of time into it. So with that, thanks a lot. And the obvious thing is this is an invitation. If you want to help, if you want to contribute, by now it's a big enough platform that if you want to give your research more exposure, then probably AutoGluon would be one thing to consider, because Hugging Face, by now there's 100,000 models there. It's hard to get noticed. With this, you get it deployed in a lot of places. Okay, and yeah, there's a lot. We need a lot of help. Okay. So with that, thanks a lot. And I know this was quite high level because I had a lot of ground to cover. Yeah, I'm happy to go into details. Yes. Sorry, what? Yeah, one step. Yes. Yeah. One of these two is the aggregator. That's very. Okay. Yeah. Let go. Okay. So yep. Okay, basically the aggregator in this case is, for instance, any run-of-the-mill, tabular AutoML tool, right? So you might have a boosting algorithm, or you might have a deep network, or you might have a tab PFN, later on just combining things. So if you look at any of the multiple towers models, right, that are quite popular, they do a similar cheap trick at the last level. And it's often quite unsatisfactory when you read those papers. It's like, and that's it. And yeah, unfortunately, yes, that's it. That actually works quite well. But I would imagine that there's probably something more interesting in between those two pieces. For instance, if you look at how Flamingo or Clip and similar things integrate multimodal tools, there might be better ways of playing with attention, or the perceiver might be better strategy. Part of the problem is that it depends heavily also on how much data you have available in your AutoML problem. And if you only have hundreds to thousands of observations, then that may not be enough data to do something very sophisticated at that last level. Whereas if you have, I mean, the best example is, Clip and similar text and image models, right? You actually have billions of examples available. So you can do something fairly intelligent and non-trivial there. Whereas if you have very little data available, then, well, there's not much you can do. And that's partially, I think, the reason why we are seeing those dumb and simple models actually doing very well. Okay, that was a good question. Yes. Sorry. Let me move again. Okay, let me move to the front again. So let's repeat the question. So the question is, what do we do with different learning rates? Okay, first of all, we cheat, right? We cheat insofar as, we happily grab pre-trained models from Hugging Face, right? So for images or text or whatever. So that's the big, that's the promise of foundation model. You already have something that's reasonably well suited for that specific domain. Now, on top of that, if you have, XGBoost or other things, I mean, they have their own parameters, they get set once and then just deployed by default for everything. The magic really happens scrutiny on something. We found that it's a lot more effective to spend your compute budget on something different solutions than on finding the best parameters for any single individual solution, right? So this makes us super weird by the standards of pretty much everybody else who does AutoML, because everybody else seems to be obsessed with finding that one single basic model, whereas we just take everything and throw it all together, and the latter works better. Right? Well, you actually. Okay, so this is so it depends on which variant. So for instance, let's take tabular. So for tabular, you go and take your boosted version or your FastPFN or your FastAI NLP version, or we have about 20 different models. Each of them is trained on its own. On the appropriately back splits, then you take those outputs and use them to train the other next layer. Now, the reason why you get a lot of extra features, and by appropriately partitioning, you make sure that you don't suffer from training on things. You retain the condition, right? So you're using the model trained on chunk A to predict on chunk B, and thus the predictions on chunk B are conditionally independent of the labels that you're actually observing on chunk B, obviously conditional, right? You use that for another thing, bagging around, and then the end goes on. They just take linear computation, right? So this way, you can trivially parallelize things, because you can parallelize over the code, you can parallelize over the algorithms. So this is why I said we didn't do anything terribly intelligent in terms of parallelization, because the problem is trivially parallel. Right? Now, once you go to only deep networks, things are a little bit different. So if you, for instance, want out probably a fixed problem, like what I showed you, graph, yes, some hyperparameter tuning and so on is required. Unfortunately, there we are back to everything else is, but it's still do a decent job just by again, picking a lot of different fine-tuning strategies as opposed to picking one single base strategy, right? And so here we are, if nothing else that we should take on with is almost certainly for the problem that you're solving, there's not one single best strategy, but you will almost invariably be better by a lot of different ones. I know this is anathema to what anybody has to do in their PhD thesis, because you have to go and come up with that one single tool that beats them all and that's better than everything else. But unfortunately, reality is a bit different. So, yeah. Yeah. Okay, so running real time. There's no in principle obstacle as long as you train it in such a way that the overall compute budget for inference fits within, your 1 or 10 milliseconds or 100 milliseconds envelope, whatever, that constraint is, right? And we have some tools by which you can keep the inference time low. One is automation installation. The other one is you just limit, how many models you ensemble over, because the more models you have, the longer it takes. And so this is, for instance, if you look at the various speed settings that we have, we just preferentially pick some models over others. If fast inference speed is a massive concern. But there's a much more exciting problem, namely the online setting where the model actually needs to update. This is something where still a lot of interesting research could be done. That's basically also what I referred to with the prediction endpoint. We can talk about that offline after this talk, but basically one of the problems is that a lot of the online algorithms, as soon as you start stacking, fail. And with fail, I mean, let's assume I have two algorithms. I have algorithm A and algorithm B. And I have a perfect online learning algorithm for, implementation for algorithm A. Algorithm using more than algorithm to change. So for A, I have a perfect online implementation, and it actually works in such a way that I will get, very basic behavior. Now, model B that sits on top of it uses the outputs of model A. And as model A changes, the outputs will also change. But since I don't necessarily go back and retroactively recompute the output, right? I will now have a concept shift or concept drift for the inputs of model B. So even if I have the perfect algorithm for A, I'm immediately screwed for B. It turns out that pretty much the best thing you can then do is just occasionally just restart and redo B. So you'll basically have, and that works out okay, and you actually don't lose more than that constant fraction of the problem. So as long as you can train faster than your data arrives, right? Doesn't have to be much faster, but at least it has to be a multiple less than 1. What you just do is you just keep on retraining at the different stages of the cascade, and you can actually work out something. So we just publish this thing big and for higher priority. It's actually in use in 100 projects inside Amazon, and so people there just kept on testing out other problems that were worse for them. There's, I think, still some interesting analysis that can also be done. There's also the method then once you have dependent random variables. So then you, like time series, other things, then you need to worry about,